Hello and welcome to the next episode of How to Make an Operating System in Rust on aarch64. Today's topic is something that we should have done quite a while ago actually. It's going to be exceptions. So for that we are going to make a file called exception.s. And the first thing is, what are exceptions? Exceptions are basically different events that can occur while the process is running. That can include things like interrupt. It can be some sort of fault. It can be a synchronous exception. Like a synchronous exception is stuff like a data abort when we access, or instruction abort when we access invalid memory. It can be a supervisor call and things like those. So to get started with the exceptions, what I'm going to do is I'm going to define two macros. One is going to be called saverex, and the other one is going to be called restore rex. And what are we going to do? So what we need to do, since exceptions will interrupt our code, we need to save the state before we do anything else. So to do that, what we're going to do is we're going to subtract from the stack pointer 192 bytes. And that gives us space for, let's see. And now here we say Python 192 divided by 8. That gives us space for 24 variables. Okay, so now what we're going to do here is we are going to say stp for store pair, and we're going to store x0, x1, and then we are going to increment the stack pointer, or rather at stack pointer 0. We already allocated all of it. So stack pointer at 0 is going to be these two registers. They are both 8 bytes, which means we need to advance 16 bytes if we want to store the next thing. So what we then want to do is we want to store x2, x3, and do the same thing. SP, but this time 16. And that we are going to do for many of the registers. So here x4, x5, 6, 7, 8, 9, and 11, 12, 13, 14, 15, 16, and 17, 18, and then we're going to make a jump to 29. Why are we making a jump? Because per calling convention, or Rust code is going to follow the calling convention. These are all the registers that are by calling convention caller saved, which means before we call a function, we need to save them. Since we're using Rust to handle exceptions, it's going to follow the calling convention, which means the other registers are callee saved, which means Rust is going to take care of saving these registers before using them. Okay. Let's see. Do we need anything else? Not for now. So we're going to adjust 16. This is 32, 48, 64, 80, 96, 112, 128, 144. Okay, and now what we want to do, I want to get some registers in addition to that, which is specifically the ELR, the ESR, and the FAR. ELR is the exception link register, which shows you the address of the instruction that caused the exception. ESR is the exception syndrome register, which shows you the cause of an exception. So is it a supervisor call, a data abort, an unknown instruction, and so on. And the FAR is the fault address register, which is going to be important when we turn on the MMU, the memory management unit. It's going to contain the address of the that caused the fault if we read or write to a non-mapped address. So let's do that. What we're going to say is we're going to say MRS into X0, since we already saved X0, that's fine. ELR, EL1, and we're going to store a pair of X30, which is the link register, and 29 is the frame pointer. And here we're going to say X0 to stack pointer and 160 offset. And now we're going to get the other two registers. So into X0, I want ESR EL1, and into X1, I want the FAR EL1. And then we're going to store them the same way. So X0, X1, stack pointer, 176. Okay. And then our function is going to take the stack pointer as an argument. So we're going to do move X0 SP. So like this, we have access to every variable that we just saved on the stack via the first argument to our function. So this is what we're going to do for the save regs, and the restore regs is the exact same thing, just in reverse, basically. So I'm going to paste that here. So we're doing exactly the same thing. All the general purpose registers that we saved, we're gonna load into the specific registers and then add to the stack pointer. Okay, we don't need to restore these three because these are normally not used in the normal program. Now we need to define something called the vector table. For that, we make a section. We tell the assembler, okay, it's going to be in the section text, and we're going to align everything to hex 800 and give it a label of vector table EL1. Okay, now we have a different, let's see, we have different vector table things. What's it called? Different reasons why an exception can be executed, and these reasons are basically predefined by ARM. So what we saw before is hex 200 was a so-called synchronous exception, which means that an instruction costing exception. So it's not something that is asynchronous, something that is not related to OR code, but an instruction that was executed caused the fault. So, and what that means is we have different labels that we need to define. So for example, the first one would be the current ELSP0 synchronous exception. That just means that this exception, if it occurs, is gonna use the stack pointer of EL0. So that's typically not what I would want to do. I want my instructions, my exceptions to use their own stack pointer, or rather the kernel stack pointer. So what I am gonna do is I'm just gonna copy and paste, because it's everywhere the same code. And we're gonna go through it. So we go from here to here. And let's just copy and paste this, and then we're gonna go through this because it's very repetitive. So I specified 2 macros to make the code reuse a little bit less. So what we have save regs, then we branch link to either unhandled exception vector, or if we actually handle this kind of exception, let's see, we're gonna branch into the exception handler. And this is the hex 200 exception. So the exception handler for a synchronous exception from the current exception level using the current stack pointer. Okay, so it's basically everywhere the same code. We have either unhandled exception vector, or we branch to our exception handler. Let's see, for the interrupts, we have an IRQ handler. And yeah, at the end of everything, we are going to execute an ERET instruction, which means exception return. So it will just return to the lower exception level and then resume the code that was already running. That is it for the exceptions. As for the exception vector table, now we're gonna make the Rust part of it, exception.rs. And in the Rust part, we're gonna define the following. We are going to define the stack frame that we just specified. So if we look at our exception.s, we specified that in this order, x0, x1, x2, x3, x4, x5, and so on, they're all gonna be at this order on the stack. And we are going to take this and make a struct out of this. So I already prepared that too. This is the struct that we're gonna use. And it's important that every variable is in this exact order. Good. Now, what we can do is we can define our exception handler function, since we are calling it. So we're gonna say no mangle, and let's see, I want to inline always. Let's try that for now. Up extern, it's gonna use the C calling convention, and it's gonna take a frame, which is a pointer, the stack pointer that we put in x0 of exception frame. And all we are going to do here is we are gonna call another function. We're gonna say exception, and we're gonna pass a mutable reference to the frame. That is all we're gonna do here. The next thing is gonna be the exception function, and here we're gonna take the frame, mutable reference to exception frame. And now that we're here, we can do the following. We can say on the ESR, so let EC, which is the exception code, exception cause, I mean. It's in U8. We're gonna say frame.esr exception syndrome register shifted by 26 and ANDed by 0b 1, 2, 3, 4, 5, 6. It's a 6-bit variable. So we're gonna actually put this like this. And then we are going to say as U8, since we have a U8 variable. And now when we have an exception, we should be able to print line exception taken, and we are going to print the EC. Well, let's actually print the EC in hex. Okay. To test if all of this is working, what we're going to do in main, we are going to say if it's CPU 0, we are just going to do an ASM supervisor call with the number 0 for now. Okay, and that should build. Yes. We also, of course, one thing that I forgot real quick, you need to mod. And another thing that we need to do is in boot.s, before we call main, we have to put the exception vector into our register, which is going to be the vbar el1. So what we're going to do is address. Let's see, are we using x7? We are not using x7 anymore. So vector table el1. This is the label that we defined earlier. And it's gonna say msr vbar el1 x7. With this, set up exception vector. With this, we have set up the exceptions. We can try to build it again. Okay. We have an undefined symbol. We actually need to put this into our linker script. So, let's see, what are we going to do? We have cargo clean. Let's clean this. Let's see, what is going wrong? Vector table el1, exception.s, section tag, vector table el1. Let's see. Of course, we need to include all of this into the exception.rs, of course. Let's just put it here. Global ASM, just like we included the other thing. Include str exception.s. And then at the start, we are going to use for aarch global ASM. Okay. Maybe this needs to go into the main. So what we're gonna do is we are going to go to exception rs. Gonna get this. Go to main, search our global ASM. We're gonna paste it here. Okay. And we got this. We are also gonna do the same for the IAQ handler. So it's just going to be the same thing. Pop extern C fn irq handler frame mute exception frame. And this function is not going to do anything for now. Unhandled exception vector, same thing. We are going to say if the exception handler, if it's unhandled, pop extern C fn. We are also going to take the frame and we will just not do anything for now. Or maybe we can say like got unhandled exception. And here we're going to do the same. We're just going to print got aarch. Okay. Unhandled exception vector, of course. Unhandled exception vector. Let's see. Where is the problem? Oh yeah. The problem is that we don't need to know mangle. And here also. No mangle. And now it builds again. So we try to run. And we say exception taken this. Okay. Which means our exception vector is working. What we now can do is we can say a print line. We are going to print debug print the frame. And now we see the exception frame. We see exactly, this is where, and also let's print it in hex. That would be more readable. Okay. Yeah, now we can see that the exception link register at this instruction caused an exception. So let's actually object dump the target my .os less, and we are going to take note of this 2900, and now we go 2900 here, and we see just before our 2900, it's always gonna point to the instruction after the one causing the fault. We see that it's our supervisor call. So that confirms that exceptions are working. And yeah, now we can try to, now we can handle exceptions when they occur. But the actual handling of exceptions is going to be in another episode. And this is all that I wanted to do for this episode. Thank you for watching and see you in the next one.